You're better off losing your hand than having it paralyzed. You see, if I am unfortunate enough to have my hand amputated, I'm not limited to a bunch of cosmetic devices all the way up to myoelectrically driven devices. But if I still have my hand and it's paralyzed, then functionally I'm in the same position, but now the commercial devices that are available are limited to one or two. My name is Martin Burns, and I'll be presenting how my research under Dr. Vinjamuri is aimed to help these people. There are 800,000 people who suffer from a stroke every year, 610 of which are first occurrences. Out of those people, 26% will lose sufficient hand function to where they need some form of assistance to go about their daily lives. If they don't have loved ones around them who can help them make up this functional difference, then they're looking at hiring professional nurses or having to live in an assisted living facility for $20K a year or $40K, which I believe are conservative numbers. My research is to design a smart, dexterous hand exoskeleton, which is worn by people who suffer from a stroke and lose hand function as a result. The idea is to reduce cost of living by improving their quality of life and independence. We do this in our lab by leveraging machine learning, biomechanics, and soft robotics to produce this prototype, Hexos 2. This system features a bio-inspired machine learning algorithm which reads muscle activity from the healthy arm and processes it with a neural network to actuate this exoskeleton using biomechanically significant motion profiles. The glove itself over here weighs about half the mass of the human hand and can independently control 10 different joints across the hand. The system is currently mechanically robust enough for us to run a study featuring healthy and stroke subjects shown here. Our subject here trains the neural network by pairing up the exo motions that we want with the muscle activities that we measure from the arm during certain tasks. We train them in individual motions and in combined motions to replicate some basic hand grasps that they use in object grasping. From there, we go into online object grasping, where they grasp different objects that are similar to what you grasp in daily life, including an eraser here, which requires a small dexterous pinch, and our system allows the subject to operate at inflection and extension. We go all the way up to heavy objects of activities of daily living, including this spray bottle, which has a complicated geometry that our exoskeleton is dexterous enough to wrap around and close and grip, while being mechanically robust enough to lift the object, which weighs about 2 pounds, off the table and put it down again. Our novelty is in our bio-inspired control mechanism, which leverages biomechanics and machine learning to reduce the complexity of controlling major devices. This is a big problem in prosthetics, which has applicability not only to wearable robotics, but to prosthetics as well. Our applications and our target market includes individuals with stroke, obviously, as well as the clinical professionals around them who are responsible for prescribing and recommending these systems, and biomedical companies which may be interested in our algorithms for separate applications. The current market is occupied predominantly with rehab companies, along with Bioservo and Myomo, which are the current commercial companies in the market with their one or two products, which, if you ask me personally, I would say they don't offer the kind of dexterity that we do. As far as intellectual property, we're poised to enter the market featuring 3 patents, one of which is a full patent which is already filed, and 2 are provisional patents which are currently in the works and close to being filed as well. Potential research partners to help us get this work up to the next level include several government agencies as well as patient advocacy groups to help us advance the technology. Thank you for your time. And once again, my name is Marty Burns. Sure.
Yeah. So just compare yours and with some others existing in the market. What is the major value of yours?
So the major value is that other devices on the market will actuate something like a simple open-close of the hand, whereas we allow individual control of the different digits, and we have enough resolution to be able to finely control individual joints of the hand. We kind of increase the complexity of the device in that way, and we decrease the complexity for the user by using our biomechanics research in the lab along with machine learning to kind of take the difficulty off of the user.
What is the weight of the device?
So the part worn on the person's hand weighs 250 grams, which is about half the mass of the human hand. And then the actuator block weighs about 4 pounds, which is something that can be mounted on a wheelchair or will be reduced in the future in size and weight, so that could be worn as a backpack or a waist strap. Yes.
How long does it take for a user to be able to manipulate the hand to train the actions?
Someone who's used to using the system can train it up in under half an hour, and then it stays robust enough to do object grasping for the rest of the experiment as far as we've run it.
Why do you think complexity is a good thing?
So complexity allows us to, it allows us as researchers the ability to tune the system how we want, but the complexity allows us to fit the biomechanics that we've identified as important to object grasping and activities of daily living. So the complexity that we add in allows us to impose certain constraints on the system that allows it to be almost ironically easier to control than a very basic device.
That'll be our last question. Thank you very much, Morty.
Thank you.